Hello everyone. In this series of videos, we're going to be looking at one-dimensional kinematics. So we will begin our study of mechanics with straight line motion. And in this part, we're going to be looking at average speed, velocity, and acceleration. So what we're trying to get out of this segment is to look at how we describe straight line motion in terms of average and instantaneous velocity and average and instantaneous acceleration. And we also want to look at how to interpret graphs of position, velocity, and acceleration versus time. So we'll start with average speed, and it just describes how fast a particle is moving. So you may remember this from a prior course or just from kind of thinking about things, but it's just simply distance divided by time. Now, average velocity, on the other hand, describes how fast displacement is changing with respect to time. The difference being that speed is always positive because distance, or how far you travel, is always positive. And as a matter of fact, speed is a scalar, and velocity is a vector. And the sign of this will give us the direction. And typically we'll put a vector over this to show that that's a vector quantity. We can also define an average acceleration, which describes how fast the velocity is changing with respect to time. And average velocity, notice that what we're doing is we're taking a change in distance over a change in time, and then taking a change of that. And actually, this also needs arrows because average acceleration is also a vector. And the sign of this will tell us the direction. Again, we're just going in one dimension, so we're only talking about positive or negative. So for example, we have a motorist that's going to drive north at 20 meters per second for 20 kilometers, so that's 2,000 meters. And then they're going to go north at 20 meters per second for north at 30 meters per second for another 20 kilometers. So what's the average velocity? Well, you might think that you can just take 20 plus 30 and add them up and divide by 2 to get the average velocity. But that's not correct because average velocity is total displacement over total time. And in order to solve that, we need to find what this total displacement is and the total time. So displacement is easy. It's just 20 plus 20 or 40 kilometers. And we'll put a plus sign to indicate direction. And the time is pretty easy. For each of these segments, the time is going to be, if we think about it, since delta x is v delta t from here, we can rearrange that to get delta t is equal to delta x over v. I could have also rearranged this guy. So for my first segment, if I'm going 20 meters per second for 2,000 meters, then I have a delta t of 2,000 meters over 20 meters per second. We'll call that delta t1, so 100 seconds. And then delta t2 is going to be another 20 kilometers or 2,000 meters, but this time divide by 30 meters per second, and that's going to be approximately 66.7 seconds. So now we can apply our equation that V average is delta x, or plus 40 kilometers, divided by 166.7 seconds. And if you like, we can convert that into meters. So that's just 40,000 meters over 167 seconds or thereabouts. And we get about plus 24 meters per second. So north, as given by this problem. And so again, the key understanding here is that we can't just average out the two speeds. We have to take into account the fact that average velocity is a weighted average, that we're not traveling 30 meters per second for as long as we traveled 20 meters per second. So it's actually less than 25. Okay, so now what if it takes the motorist 1 minute to change his speed from 20 meters per second to 30 meters per second? What is our average acceleration? So our definition of average acceleration is a change in velocity divided by change in time. So that's going to be v final minus v initial divided by delta t. Now, sometimes I'll write a v naught as initial, and sometimes I'll write a vi. It means the same thing. Whoops. And this tablet that I'm working on is a little touchy, so if it advances a slide, I'll just go back. So 30 meters per second is v final, and v initial is 20 meters per second, and this happens in 1 minute, which is 60 seconds. So that means that my acceleration is about 0.17 meters per second squared, and again, it's north, going off the previous example. Okay, so now we're going to start looking at graphing motion, and you can see that if this is a graph of position x versus time, and I pick 2 points A and B, that I can find a slope by considering delta x over delta t, which we have defined as the average speed. So therefore, the slope of x versus t is v average. Okay? Now what do you do if you have a graph that has a curve to it? Well, that's no different. We just draw a line between the 2 points and we calculate the slope. Now in this case, and also in the other case, notice that velocity has units of meters per second, and x is in meters and time is in seconds. So if we divide meters by seconds, we can see that truly the slope of the graph is going to give us the average velocity. Average acceleration can be determined from a velocity versus time graph. We do much the same thing. We plot 2 points and we look at the slope, which is delta v over delta t, and this is meters per second and this is seconds. So that means that the acceleration will have units of meters per second, which is often known as meters per second squared. However, if you write it as meters per second, this gives you a better insight into the fact that the velocity is changing. Okay, so we want to find in this example problem the average velocity for the particle as it moves from point A to point B. Now, if I ask to find the average speed, that would be a bit trickier, and we'll come back to that in a second. But the average velocity is very easy to figure out. It's just simply delta x over delta t for this graph. So it's going to be x final minus x initial over delta t. And x final we can see is a value of -1. X initial was 0, and delta t was 0.5 seconds. So that means that v average is -1/2. -1 divided by half is actually -2 meters per second. And you'll note that if we draw hopefully a straight line from A to B, that actually has a slope of -2. Okay, now that was easy because average velocity really doesn't care about the fact that we're going forward and then we stop and we turn around and come back. Average velocity only depends on the starting and ending position. Okay, now from this graph, if we want to find the average speed, this is a little bit trickier, and we can take delta x over delta t by noting that what the object does is it goes to about, we'll call that approximately 1.8, and then it travels backwards. Oh, that was unfortunate. So it travels forward plus 1.8, and then it travels backwards about -2.8. So if we call this point C, imagine that a car is going forwards 1.8 meters to get to C. and then it stops and turns around and travels an additional 2.8 meters to get to B. So that means that the total distance traveled is really 4.6 meters divided by 0.5 seconds, so that's 9.2 meters per second. And that's positive because average speed is always positive. Okay, so next time we're going to talk about, well, how do we find the velocity or the acceleration at a specific point in time? So how do we find instantaneous velocity and acceleration?